So let's start with our first objective, DNSSEC, the security of DNS. Remember we talked about DNS, what DNS does, and the second objective then will be BGP, the routing infrastructure. But for DNS, it's all about securing the names. DNS, in the end, delivers you an IP address when you give it a name. So what is the problem here? So if you look, that was our example for DNS, and you want to transfer money, for example, then you ask your name server of the ISP typically has a cached content. If not, then we learned how to access root servers, how top-level domain servers, authoritative name servers of the bank, etc. And they can all send you back an answer. The problem is all the answers can be wrong. So they can all lie. So maybe the authoritative name server of the bank most likely will not lie, could be compromised, but all the others, they could simply lie. And why? Well, main reason is, think of the original RFC about DNS, the main reason is that the main idea, as the inventor says, of the DNS system is that everyone can get a chunk of the namespace and can manage as they choose. Okay, that's nice. However, you aren't supposed to lie about other parts. So in the end, meta rule was if you must lie, lie only to yourself. But what happens if you lie about other parts of the namespace? So the problem is that this guideline does not comply anymore with all the malicious activities in the internet. Because in the very beginning, there was no commercial interest. Now there's a lot of commercial interest, illegal interest, etc. in the internet. So it's not a pure research network anymore. So what could happen? The DNS resolver can lie about the DNS answer. And the problem on your side is your client cannot verify the correctness. So if you get an answer, you have to trust the answer. But why should you trust the answer? So all the resolvers, they can simply lie. Okay, so something has to be done. And that's exactly what all this DNSSEC is about. So the overall goal is provide integrity to prevent spoofing and poisoning. Spoofing and poisoning, so that means you alter answers, for example, or you poison caches, DNS caches. What is the approach? Authenticating messages so that you know, okay, this message really originates from a name server you trust, so no one on the way changed the DNS content. That's the first thing to do. And also authenticate resource records. Remember resource records, that's where we stored the information. So we have to be able to check that the data really originally comes from the authoritative DNS server. We learned we have, for load balancing, many non-authoritative name servers in between. Okay, so that's a problem. There are other things that could be done. So what about denial of service attacks and things like this? There are some other goals like hiding data and hiding requests and authorization, who is allowed to request and to answer, and so on and so on. Not the goals. So we will focus on the two goals, authenticating messages and authenticating resource records. There are many RFCs handling this, starting with the 4033, 3435 about introduction, resource records, and the protocol, and many updates up to today. So some fundamentals. DNSSEC is based on public-private key cryptography, so asymmetric, and introduces new resource records. Remember resource records, we had the A records storing the addresses, for example. We had the MX records for email. Look this up in our DNS chapter. So now we have new resource records, RSIG to store the cryptographic signature, the DNS key that contains the public signing key, a hash of the DNS key, and additionally some more records that are for explicitly so-called denial of existence of DNS records certain types of attacks where you have to protect something. Child zone, I will come back to this. Updates to DS. What is the DS? I will come back to all these details. So records, parent zones, etc. So important for now is there are new entries, new resource records we have to store in the DNS servers. Two more concrete objectives of DNSSEC is we have to be able to secure a zone. And we'll talk a bit about zone delegation. So first of all, a zone. A zone, you know, someone is responsible, like DNSSEC is responsible for all the German top-level domains, or your university is responsible for then all the domains inside the university, etc. We had the zone servers, primary, secondary, etc. So securing a zone, what's important here? Well, you have to sign the resource records. So you have to make sure that all resource records are signed and no one can change them. The way DNSSEC does this is not signing individual resource records, but to form a set of resource records. And on the next slide, I will show how these sets are formed. So for example, to bring together all the resource records that are related to the addresses, IPv6 address, for example, bring them together, and this makes a resource record set, and then you can sign the set, or all the resource records about the MX records, so for the mail exchanger, and you sign the whole set. So how do you create such a set, and how do you sign this? Well, this is an example that such a set comprises all the resource records, and here showing that have an identical name, class, and type. So class, internet, it's typically all the same, but here we have address records, that was the type, and you see www, OpenDNSSEC, for example, SE. So same name, same class, same type, and then we can bring them together and sign them. Then we have this new entry, the DNS key. That's the public key that's stored there, and the public key is important, as we learned with the asymmetric cryptography. We have to know the public key, and there's also the resource record RSIG that contains the signature of this set. That's so metadata and the signature itself. So we have new elements, and we have some more, as I showed you in the table. So how is this done? Well, DNSSEC uses keys, quite obviously, but it uses two different keys. One, on the right-hand side, that's the zone signing key. That's the key that's used to sign these sets, the resource record sets in a zone. That's called the zone signing key. And then we have a KSK, a key signing key, that validates the zone signing key. So the two keys. And this key signing key operates the same way as the zone signing key. And you sign with this, the zone signing key that is stored in a DNS key. And you create this resource record signature for the DNS key. So in the end, this is the way how you make sure that the resource records are then secured, or sets of resource records. Okay, still we don't have any chains of trust, etc. This is just that, okay, we create signature for the entry. So similar to our email example, so you have your plain text, and then you can create the signature that makes sure that you are really the creator of a certain text. So you sign it. Okay, so this is why it's called signing keys. Now the other part is, okay, how do we trust? Because we learned that with DNS, we follow through several resolvers, DNS, and until maybe we get to the root, and the root doesn't do it recursively, etc., etc. How can we trust these many steps? And that's all about this chain of trust that we have to establish inside the DNS system. So DNS exactly uses this chain of trust to implement the security, and there's the root zone, and the root zone has a root zone key, and that's the highest possible key in the DNS tree. Remember, we have the root servers and then the top level domains, etc., etc. And it started 2010, so 13, 14 years ago. So there was the first signature of a DNSSEC root zone. And then starting from this root, the next lower zones followed. So November 2011, more than a quarter of the top level domains are signed. In February 2018, 98%. So the top level domains are now signed and use DNSSEC. So you start with a root, and then you point to the lower zones, and all those pointers are then validated with a zone key. And in the end, this ensures that only the root key is needed to validate all the DNSSEC keys on the internet, because if you have the root key and you can follow the chain, you can make sure that everything is fine. How this works, example in a second. So what are consequences if we say, okay, we only need the root key? So the root key must be anchored in the resolvers, either in a local computer or the next name server. So you can assume that, okay, I trust the next name server. If you can do this, different topic, but that's then the name server of your ISP typically. So when a resolver knows and trusts the zone key, then it can validate the signatures belonging to the zone. So you trust the key, okay, you know the key, you have to know it, and you trust the key, and then you can check, okay, with the key, okay, you can check all the signatures, I can trust them. And the idea is that we only have to carry the root key, or you can also have some zone keys, and then you can validate all this DNSSEC data in the internet. Okay, so that is basically the idea how you set up this chain of trust. Keys, signing in the zone, you have to trust the key, and you need the root key, because the root key, then you can follow the pointer and you can trust in the end the whole structure. So now how do you connect parent zones, children zones when it comes to trust? So we have the delegation signer, the DS record. And as I showed you in the table, the DS record, basically this is the hash of the key signing key, DNS key. And this DNS record is published in the parent zone and used to delegate the trust to the child zone. Somehow we have to establish this chain. So for example, you see here, this is this hash value, and the DS record itself is signed by the parent. That's the idea. And if you have this, if you know this hash, then you see, okay, looking at the parent, okay, how can we get then the trust to the child zone? So this is this handle for building this chain of trust. This is our handle, is this hash value. So how does it then really work, all this together? So in the end, you have your client computer, and your client computer asks for a certain URL. And then you, for example, if no one knows anything, then we learned that we have to go to the root. And together with these answers, this is what we used to do, these answers, who to ask next. So for example, this one, etc. We also get keys showing that, okay, in the end, I'm allowed to give this answer. So you can trust this answer. And then this continues as we know it until we get the answer. here from the authoritative server, and then our name server delivers this back. And as you see, there is no exchange of any keys here. So typically we have to trust our local DNS server. So this could be yours or the server of an ISP. So then your client doesn't have to do anything with DHCP. Okay, so might be still a bit confusing. How does this work with this chain? We now know the basic elements. So the different resource records and what can they do and how they sign, etc. But how does this now in the end work? Well, an example. So if you are in a zone, how can we trust data in a zone? Well, we can trust it if it's trusted by a zone signing key. Okay, only partial answer. So basically we say, okay, trust the data. Okay, you don't know anything about the data. Oh, okay, trust the zone signing key. Okay, why should we trust them? Well, you can trust them if they're signed by a key signing key. So we're still within this zone. So, okay, so now we shifted from zone signing key to key signing key. So why should we trust this one? This can be trusted if a trusted DS record points to this key. Okay, why should we trust this one? Okay, and the DS record now can be trusted if we're still in a zone, if it's signed by the parent's zone signing key. So this is, you see, when we go one level up, so if it's signed by the parents, or, well, if it's exchanged out of band. So we shifted this exactly in this moment. We shifted it one level up, so if signed by the parents. And now, why should we trust the zone signing key of the parents? Well, if, and then we go from parent to parent to parent until we reach the root. And why should we trust the root? Remember, we have the key of the root. Okay, so this is one way of basically going up this trust chain. Here a bit more concrete example. So the root of trust, as I said, is the key signing key really for the DNS root. And you have to know this. So that this is this initial trust you have to have. That's true for all these. There are also certificate for email signing, for encrypted online banking, etc. So there must be some root certificates you simply trust. Okay, so if you have this address, for example.com, then you see how well you can go up with zone signing key, DNS key, etc., and then key signing key, and then you go exactly this level up, because we know that in the next higher level someone points to this example.com. Then within the level we continue, and then okay, we go one level up, someone points to this example.com until we reach the root key. So this is how we can establish this trust chain. Okay, what about the deployment of all of this? So how can this be done? There are different options for the clients. So on the client, you can have a full DNSSEC resolver. That's possible, as I said. And so it's fully compliant. And then you can do the DNSSEC validation on your own. So that's one way of doing it. Then there's also another version, which quite often is done. We have so-called stub resolvers. So basically on end systems, so you trust completely the server, so from the ISP. And now the client can decide how to handle unauthenticated data. and this is the typical deployment model. So you can enforce the server to perform validation. If it fails, you can always think what you do, and then the server performs it or answers with an error, and you can decide if you need or not the authentication. So that's one way of doing so. You don't have to have a full DNSSEC resolver. What about the deployment statistics? So current statistics from 24 end of January shows that, okay, we are up to, this looks nice, .com, for example, to several millions. Okay, with a slight problem here. Also .net goes up, looks good, really? Look here, that's the percentage. The percentage of the domain names that really use DNSSEC. That's not that much. I mean, we're here around 5-point-something% of the .net and 4% of .com. So this is not really good. Why is this the case? Questions. So, starting here, check the current deployment situation of DNSSEC. So what could be reasons? Why don't we have 100%? Why is not always everyone happy using DNSSEC? Or there can be many different reasons. But starting from the top, so why is DNS vulnerable? Think of the history. And what is the idea of DNSSEC? DNSSEC doesn't solve everything, but some of the problems. And what is this chain of trust? How do you secure a zone and then going up and down? And what is this chain of trust? What is the basic idea here?